Today we're going to examine how we measure the level of volatile organic chemicals there are in an environment. Okay, so a lot of different kinds of environment that you might be concerned about VOCs. For instance, in a workplace, right, you might be concerned about solvents that a worker is exposed to. A volatile organic compound is any compound that contains carbon, that's the organic part. Any compound containing a carbon molecule is considered organic. Volatile means that it has a partial pressure that's low enough that, or high enough, so that it's likely to evaporate into the air. Now, this piece of plastic has a partial pressure also. In other words, there's a rate at which this will evaporate into the air at the temperature, room temperature. Its partial pressure is super low. So it literally is not evaporating. It literally is evaporating into the air very slowly, maybe a couple of molecules every hour or something like that. In France, they have a Bureau of International Standards where they maintained this platinum ball that was the standard kilogram. And that's been there for like 70 years or 80 years or something like that. They remeasured it very carefully, and it was actually something like 50 micrograms short of a true kilogram. So apparently, over that long period of time, a little bit of that material was lost. But most things, this table, they're not evaporating much stuff into the air. That platinum ball not evaporating anything significant into the air. Unlike that, many of these organic compounds have partial pressures that are relatively high. So they will evaporate into the air and contaminate the air, so you can breathe them. So you can wind up breathing these things. In fact, you can calculate what would be an equilibrium or if you know what the partial pressure is at a certain temperature. You can figure out that if I spilled acetone in here and closed the door and sealed the room up, what the concentration in the room would become. How much of it would be air, how much of it would be whatever I spilled in here, acetone or something like that. You can actually figure that out, okay, based on that partial pressure. So volatile organic compounds not the only thing that have partial pressure. There are a couple of metals that have a relatively high partial pressure. Anybody know what they might be? Mercury, right? Mercury literally will evaporate into the air. So if you spill mercury onto a hard floor somewhere and you clean it up, and there's techniques that they use to clean it up so they capture it safely and so on and so forth. You can contain the hazard. But if you spill it on carpeting like this and it soaks into the carpeting or it gets to the cracks in the floor or something like that, it will continue to evaporate into the air for a considerable period of time, right, until it's gone. Right, so the air now will be contaminated with mercury. So that's why a mercury spill is such a big deal. Years ago, we used to, in mechanical rooms, we used to use mercury. In fact, in your home, your thermostat in your home used to be often a mercury switch, a little ball of mercury that's in a little tube that bridges a pair of wires when the temperature is satisfied, and it's connected to a coil, a metal coil. So as the temperature goes up, that metal coil uncoils, that tips and breaks that connection so that the temperature is controlled. You can control what the angle is of that little glass vial. And it used to be in most homes, these mercury switches. Nowadays, you don't see them anymore. Now that's considered a hazardous waste, right? When I was a kid, anybody have an instance where they had to deal with mercury in a house or work or something like that? No, you guys a different generation. I used to see it all over the place. Yeah. Was it in a home or anything like that, or? Yeah, mercury thermometers. Yeah, exactly. There probably a lot of people still have them around somewhere in the garage or a basement or something like that.
I see them at work stuff. There's still stuff at work too.
Yeah.
Plenty of barometer cups still around there.
There you go. And how about a doctor's office? Where do they use mercury in a doctor's office? The blood pressure, exactly. That's the that's a gold standard for blood pressure. You don't even have to calibrate it, right? Because you know that when the column of mercury reaches that height, you know what the pressure is, right? You don't have to worry about that. If it's that much, if it's 100 millimeters of mercury, that's what the blood pressure is, right? Because gravity determines, like physics and gravity determine what the height of that column is. If you use the electronic ones now, with the electronic pressure sensors and so on and so forth, they have to be calibrated, because you can't be sure they're going to, it's not a matter, a lot of things are going on there in that sensor. It could change resistance and it could change and so on and so forth over time. So those have to be calibrated. But a mercury, blood pressure, yeah, and there's a name for it. What, I'm sorry?
Dental amalgam.
Oh, dental amalgams used to have mercury in them. They were in there to, I think, so they were more machinable or something like that. Right? And a lot of people have that removed over time because they're concerned about it. I'm not so sure that, ingesting the mercury molecule probably just passes through your body. Most likely, it's probably not quite as hazardous as inhaling the mercury is. Right? But that's, that could be wrong on that. There could be new research on that or something like that. Oh, yeah, then the dentist, and you sure, of course. Yeah, well, again, now you have a whole different situation where you deal with an occupational hazard where you're exposed to it continuously over 8 hours a day over working life and so on. But then there's also exposures to volatile organic compounds that can take place in your home as well. So you have cleaning chemicals, right? If you smell them, they're getting into the air and you're actually, they're volatile. A lot of them you don't smell quite as, or don't smell good, but they can be pretty hazardous. A lot of paint solvents and so on and so forth. Certain materials, new furnishings, new carpeting can off gas, and you can get that new carpeting smell, that new home smell. A new car smell is basically VOCs evaporating off those plastics. And eventually it goes away because most of these things have a half-life. Over a period of time, as it evaporates out, it's drying out. Well, those materials that are volatile are getting into the air and they're leaving that material. So after a year or so, you don't smell that new car smell anymore. I remember they used to sell like a little spray. You could spray in a car, make it smell like a new car again, right? Hopefully not using the same chemicals that they had in the original plastics and stuff like that. When I was a kid, we used to have these, how I like to have these little puzzles where there's a little ball, little steel ball, and you can make it go through a maze and so on and so forth and fall into a little pocket at the end. When I was a kid, we had those and they had mercury balls in them. So literally you would run through it. And of course, by the time you got bored with it, you'd break it open and play with the mercury. Right. So my generation is exposed to a lot more hazards as kids than you guys are. Okay. So now we have VOCs, organic. These chemicals could be acid in the nail salon, might be acetone in a doctor's office. It could be isopropyl alcohol used as a disinfectant. It could be anybody work with dialysis machines, for instance, or in colonoscopies or anything like that, endoscopic salons. Anybody work in those? They use for dialysis equipment, for endoscopic equipment, they use glutaraldehyde as a disinfectant. It's a little bit different than formaldehyde. It's called glutaraldehyde, and they use that as a disinfectant for those machines, and the workers are exposed to those fumes. Glutaraldehyde is a exposure that can cause occupational asthma. And it also suspected carcinogen. Formaldehyde for sure is a suspected carcinogen. I think glutaraldehyde maybe as well. I'm not positive what the take on it is right at the moment. Okay, so there's a lot of these kinds of hazards around different kinds of workplaces. But in order to evaluate how much of a hazard they are, we have to understand what level they are in the air. We have to understand what the level is in the air and what the dosage is that worker is being exposed to. So since these are hazards, they're recognized hazards, OSHA has techniques. OSHA and NIOSH have techniques for sampling these things in the air. And they're the same kind of NIOSH standard that we look at for particulates and for asbestos fibers and so on and so forth. So we're going to take a look at those now. These are kind of hard to read right now, but at that size, when you get a chance they're actually on Blackboard. You can download them. Or you can just go online and just Google NIOSH standards, NIOSH methods and standards, and you'll find a list of all of these, an alphabetical list that you can go through for any different chemical you might be interested in analyzing for. So on the left is standard 1501. It's for hydrocarbons. I don't know if it's easy for me to increase the size of this. Let me see if I can get it. That won't let me do it. So that includes, among other things, You can probably see this better than I can. Benzene, toluene, xylene, and so on and so forth. That's that class of particular compounds, right? And it lists the ones that this method is to be used for. And how does it work? Well, it tells you what kind of sampler you have to use. And it's a solid sorbent tube with 100 milligrams of activated charcoal. And it tells you what the flow rate should be. It's actually on another table. It tells you what volume of air you need to sample. It tells you what temperatures you got to work out, how many blanks you need. And then on the right-hand side, it tells you how the sample should be measured when you're done. Instead of weighing it now, you have to figure out how much of this material got absorbed into this device that you use to capture it from the air. And for that, use gas chromatography. So typically it would go to a lab unless you are working in a situation where you have such a lab, and it describes what kind of equipment you need and so on and so forth. On the right here, there's another method 1400. It's for alcohols. So for instance, ethyl alcohol, isopropyl alcohol, and so on and so forth would use this method. Why are they different? Might be a different kind of sorbent material. Might be that for this particular material, you have to have a different flow rate because it's not absorbed by the sorbent as easily. So you can't have the velocity of air going through it too fast, or it won't get absorbed and so on. So there are reasons why these methods may vary just a little bit, but generally they're by class. This is a class alcohols, and this is a class of aromatic hydrocarbons. Anybody know what they mean by an aromatic hydrocarbons? And it's not perfume. It's not has nothing to do with the way it smells. Although a lot of aromatic hydrocarbons have distinctive odors. Anybody know what it stands for? We're going to get to that in a second. Okay, so how do these NIOSH methods work? We have pieces and parts here we're going to be looking at in a little while. But basically, what we're going to do is we're going to use a sorbent tube. And that sorbent tube is a glass tube that is packed with activated charcoal. Activated charcoal absorbs a wide variety of organic compounds. Use it to filter water. Take pesticides and solvents out of water coming into your house. If you're using a well, for instance, in your area where they do a lot of farming, you use it in your mask, in your respirator, to take organic solvents out of the air so you don't wind up breathing them. Okay, so it absorbs a wide variety of organic compounds. Okay, now there are some compounds it doesn't absorb. So for those compounds, when we're measuring those compounds, we use that same glass tube, but we put a different material in it. It might be a silica gel. It might be a plastic-like material called Tenax, right? There are different, and how do we know to use that for a particular chemical? How do we know to use that other material? Well, we look at the method, the NIOSH method. NIOSH method tells us, well, activated charcoal is not suitable for this because it doesn't absorb this material, so you should be using a sorbent tube with 10x in it. So many milligrams of 10x in it instead. So this tube contains that material. You don't see the tube in there because it's encased in a holder right now. So that tube is just a little glass tube, right? It's open at both ends. It's connected to our some tubing. And then from the tubing, it goes to a little device that's a constant pressure controller. And what that does is a little kind of grommet in there that as you're pulling air through it, if the air rate, if the rate of flow varies very much, it deflects that device in there so that it lets more air through when the pressure is low, less air through when the pressure is high, so it evens out the flow. Why didn't we use that when we were working with particulates and working with asbestos fibers? Well, the reason why we didn't use it with them is because we were working at 1 liter per minute, 2 liters per minute, 5 liters per minute, right? A lot of airflow, a vigorous airflow. When we're working with organics with this method, very frequently we're working at very low flow rates, okay, like 1/10 of a liter per minute. So we need that device to make sure that these pumps, and you'll hear them lug when they're at low volume, dun, 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 dun. It doesn't sound like a continuous flow. It sounds, because they have a little diaphragm that's squeezing the air through, right? And it's not quite as a continuous flow. So these are on here to kind of even out that flow. So they're used for VOCs when we're measuring at low flow rates. Why are we measuring at low flow rates, do you think? What do we have to make sure happens to those VOCs in the air as it goes through the activator? Exactly, it's got to be absorbed onto the media. If we blow that air through there at 5 liters per minute, the activated charcoal may not have the time to capture it, right? Absorb it as it happens, right? Won't have the time to capture it, so it'll wind up passing through there. So we won't. So we will think we have less than we really had in the air. So we need usually with these kind of analysis, we're dealing with relatively low flow rates. Okay, and then we have the pump, and you see a worker over here with this device with the sorbent tube hanging off their collar, and the pump is somewhere on their belt or something like that. Here's another look at it. In this case, this is basically the equivalent of our dry cal, right? It's measuring its calibration device, measure the flow rate. Here is our pressure equalizer. Here are our 2 activated charcoal tubes, right? We have 2 of them there. This holder has a little needle valve on it. Needle valve there and a needle valve there. So we can adjust, we can have 2 tubes running at the same time. So we can adjust one tube for 1/10 of a liter per minute, let's say, and the other tube for 2/10 of a liter per minute. Well, why is that important? Well, if we don't know what the concentration is in the air to start off with, we have a better chance at measuring the same area, 2 different flow rates, so we don't pull too little air or too much air to be able to analyze this. So very frequently you'll see a method where they're using more than one sorbent tube at the same time. So we run one pump, and we can adjust the flow rate through each of these different tubes to different rates. Okay, so widely used in manufacturing, construction, metal cleaning, painting, you name it. There's almost nowhere where we don't see these things in industry used pretty widely. Okay, so this one that we see here is a material called toluene. What does this ring represent? Okay. Yeah, that's what makes it aromatic, is the benzene ring. That's a benzene ring. That's 6 carbons in this cyclical formation, right, in this hexagon. So those 6 carbons, if this wasn't here, if that ammonia wasn't, if that methyl group wasn't here, this would just be benzene. With one methyl group, it's toluene, right? So it's just a derivative of benzene. Okay, and a lot of these derivatives of benzene are precursors for making more complicated organics, and also solvents and chemicals that are useful on their own terms. Why do I bring up toluene? Because toluene is very frequently in almost everything that you see. In fact, I spoke to a guy who does a lot of GC work and a lot of indoor air quality work, and he told me that if he didn't find a certain amount of toluene in the air, in indoor air, he usually thought there's something wrong with his machine or his sample, right? Because he almost always will detect some toluene from some source in indoor air. Smells like, in concentrated paint, smells like basically like paint thinner. Okay, here's a couple of others. Phenol, right? Only difference there is an OH instead of a methyl group. Xylene is 2 methyl groups on that benzene ring. Okay, now the nomenclature that, how many of you guys have taken organic chemistry in like the last century? Okay, good. Long time ago, I guess, for a lot of people. Okay, so you might remember that benzene ring, this is ortho. The position determines what it's called. Like this is dimethyl benzene, but when they're next to each other, it's called ortho. When they're one off, it's called meta, and when they're opposite one another, it's called para. So this would be para-dimethyl benzene. Okay, and in fact, para-dimethyl benzene is, let's see, if I don't have it here. It escapes me at the moment. It is a common solvent, though. Okay, so other common classes that are used industrially of organic chemicals, which are commonly used, are ketones. Ketones have an oxygen bond on the carbon, and then they have carbon has 4 free electrons in its outer orbit. It needs 8 to be stable. So it tends to form a double bond with oxygen. And then you can have another organic compound, two organic compounds that are connected to that carbon that's connected to the carbon. And that's called a ketone. There's a lot of common ketones. Usually the name ends in ONE, acetone, dimethyl ketone to propanone. Those basically all the same thing, right? Right, same name for the same stuff. That's acetone. Okay, so here's another one, methyl ethyl ketone, or MEK, very widely used solvent, causes liver damage, peripheral neuropathies, all sorts of other stuff. All these same names: 2-butanone, methyl ethyl ketone, MEK, and benzophenone is another one, more complicated version of a ketone. Aldehydes, very frequently come across aldehydes also. This first one, formaldehyde, right? So formic acid would be one form, if double, if you have an O and an OH on here, that would be formic acid. This is formaldehyde. Formaldehyde because you have the two hydrogen groups. Difference between ketones and aldehydes is that the ketones have the other two compounds connect besides the oxygen are other carbon groups. With aldehydes, the other two are not necessarily other carbon groups. Okay, so we have a number to formic acid, formaldehyde, acetaldehyde, acetic acid. Similar, you can see the difference between acetic acid. Acetic acid just has an OH, and acetic acid. Now, I don't remember, but there's the way you synthesize these things is one of them is a combination of an organic acid and organic salt. That doesn't really matter to us. Okay, so toluene, liver toxins, kidneys, blood system, central nervous system, irritant. It's also an irritant. It can be absorbed through the skin and through inhalation. Now, going back to the basics, dose is equal to the concentration times exposure. So time workers exposed. If he's exposed 8 hours a day, you want to determine what the average concentration is over that 8-hour workplace exposure. A lot of times you're going to be in situations where you're going to be doing area monitoring, so you may not be measuring the exposure over the full 8-hour day. You'll be looking to see if the PEL is exceeded, say, over the period of time that you think is the highest exposure on some occasions. But really, you should be considering at least measuring the worker over his entire workplace period. Average worker breathes in 10 cubic meters on an 8-hour day. Average person breathes in 20 cubic meters on a 24-hour day. The OSHA permissible exposure limit for toluene is 200 parts per million. Anybody know what the TLV is? 20, right? Quite a difference, right? 200, a tenfold difference between what ACGIH thinks is safe and what the permissible exposure limit is, right? So 200 ppm is equivalent. That concentration is equivalent to 754 milligrams per cubic meter. Those represent the same concentrations. One of them is in weight per volume of air, right? Described as weight per volume of air. The other one is described as parts per million. This is weight per volume. Parts per million is volume per volume. In other words, 200 liters of 200 ppm would be like having 200 liters of what am I talking about here? Toluene in a million liters of air. 200 parts volume to volume. So we have to do some conversion to get from this weight to these ppm. That's kind of like a basic industrial hygiene calculation. So, but at any rate, we know that at the permissible exposure limit, a worker would inhale approximately, let's see, you'd be over an 8-hour workplace exposure, you inhale 10 cubic meters of air. So if there's 754 milligrams per cubic meter, he would wind up inhaling 7.5 grams of toluene during his normal work space. That's really his dose. That's what he's really being exposed to. Okay, so yeah, here we go with our exposure limits. So, okay, basic calculations. Okay, so here's a basic conversion from ppm to milligrams per cubic meter. I think I might have gone over this like the first session or two, where you use Avogadro's number and you use what you know about the mole, what how much gas is represented in a mole liter, in a gram equivalent of a mole of material. We're not going to worry about that for right now, but basically you can convert between ppm and milligrams per liter. If you know the quantity in milligrams per liter, you can multiply by 24.45. If you remember, that's how much gas you have in 1 mole, 1 gram, the molecular weight expressed in grams. In other words, 24.45 moles of 24.45 grams of any VOC will take up that amount of space at standard temperature and pressure. So that's our conversion factor for that. So if we have 2,000 milligrams per cubic meter, multiply it by that, that gives you the volume over the molecular weight of toluene, will give you the concentration in parts per million. I forgot to turn this damn thing off again. Yeek. Watkins Glen. I don't know anybody in Watkins Glen. At least nobody I want to hear from. Okay. So if we want to go the other direction, milligrams per cubic meter, you can take the number of ppm, 1,000 let's say, times the molecular weight. For toluene it's 92, 1,000 times 92, and divide it by 22.45. It'll give you the concentration in milligrams per cubic meter. It's simple enough calculation. Okay, here's an example of it that using what we just saw. Okay, so 200 ppm times 92.14 divided by 24.45 winds up with our 754 milligrams per cubic meter, just what we were looking at before. Going the other direction, 754 milligrams per cubic meter times 24.45 over the molecular weight winds up giving us 200 parts per million. That should, what is that? What I do there? That should say ppm. That should say X ppm for each of those two. I'll fix that. Okay. What are the units for parts per million? What are units like for parts per million? It's unitless. It's liters per liters, right? So liters cancel out. Doesn't have any units, right? So it's literally just a ratio. 200 parts of this to 1,000,000 parts of that, right? No actual units. Calculation exposure dosage. Okay, so we sort that. Okay, so how are we going to use this? How is this going to be useful to us? We're going to draw a sample of air through a charcoal tube using a sampling pump. Okay, so let's say we run that pump for 8 hours at 0.21 liters per minute, right? Sorbent tube sent to the lab. Okay, so what's going to happen there? That sorbent tube is going to absorb any toluene that's in the air that's passing through it. Okay, and that we know how much air is passing through it because we know that 8 hours is 480 minutes times 0.21 liters per minute. The sorbent tube then gets sent to the lab. We know how much air we push through it. The lab then sends you a report. We've analyzed that sorbent tube you sent us, and we found in that sorbent tube 100 milligrams of toluene. That's literally what you would get back from the lab, is a report on how many milligrams or micrograms of this material they found in the sorbent, right? So now the deal now is that you need to convert that into parts per million or into milligrams per cubic meter. Problem is that it's probably would be very unusual for you have sampled exactly 1,000 liters, right? Which is a cubic meter. So if you had sampled exactly 1,000 liters, then you know that 100 milligrams is in 1,000 in a cubic meter of air. You wouldn't have to do any calculations, right? Unless you wanted to change it to ppm, and you could go back and use that formula. Problem is that it's very unlikely you're going to sample that much, number one, or that exact value, number two. So you're going to have to make an adjustment for it. If you only sampled 500 liters, in other words, half a cubic meter. You would have to double that number 100 to figure out how much is in a cubic meter. So you would have to, for whatever volume you had sampled, whatever number of minutes and flow rate you would use, you would need to make that correction. Okay, so let's do this together right now. Whoops. Okay, so I'm going to ask you guys. Let me pull up. Let me escape here. Actually, I'll do it on paper if I can. Let me get this out of the room. No, I don't want it. I don't want to lose that. This I can afford to close down here. Okay. Eek. Eek. Problem is I have all these tools, but I have no memory. Okay, I can remember these numbers. Okay. Oh, something's going wrong here. Oh, I got the wrong one. Okay, now I'm in good shape now. Okay. Of course, the recording has all my mumbling on it. Okay, so let's see. Okay, so we ran this for 8 hours. How many minutes are in 8 hours? 8 times 60, 480. 480 minutes times 0.21 liters per minute. So what volume have we sampled here? Somebody want to calculate that for me? Got a phone, calculator, anything? I could do it myself. I like you guys to get involved. How much? 100.8? 100.8 liters is the amount of air that we've sampled here, right? What fraction of a cubic meter is that? Right? Well, let's see. 100.8, yeah, that's 0.1 cubic meters. 1,000 liters, that's approximately 0.1 cubic meters. Another way to do this is to say, well, 100 liters is to 1,000 as, how many grams did we say was in there? Milligrams was in there? 100 milligrams, 100 milligrams is to the number of milligrams we would expect to be in 1,000 liters, right, or cubic meter. So I cross multiply and you get 100. X is equal to 100 times 1,000. So 100. So how many milligrams do we have in a cubic meter? We have 1,000 milligrams per cubic meter. What's that? I divided by 100 on each side. Oh, yeah. Let me get rid of that so you can see. Yeah, thanks for warning me about that. Oh, I'm using the wrong mouse. Okay. All right. It makes sense though, right? Because we had, how many milligrams did we say? We had 100 milligram at 1/10 of a cubic meter. So obviously it's going to be 10 times as much to figure it out. Now, the numbers are going to work out when you actually do this. I kind of like cheated, right? Because I made the numbers easy. But you can see if you set up that ratio, you can always figure out how much would have been in a cubic meter of air if you had sampled a full cubic meter of air. So now that we know that, how do we calculate how much, what the concentration is in ppm so we can compare it to the TLV or to the permissible exposure limit? Well, I'm going to go back to our formula. If I can find it again.
And G slash.
There it is. No, that's not it.
Divided by.
Yeah, let me go back to it. Here we go. Okay. So we want to find how many ppm we have. So it's going to be equal to the milligrams per cubic meter, which is 1,000 times 22.4 over the molecular weight of toluene. Anybody remember what that was? 92.14. Anybody want to calculate that for me? Yeah, you can use 24.45. I hate you. You want to know very briefly? I'm glad you did that. I'm glad you brought that up because I think we need to have an important discussion about significant digits. And this causes so much confusion. I have no idea how many questions I get in biostatistics about, well, how many decimal places should I give you the answer to, and so on and so forth. I'm glad. I really am glad you brought that up. What did it come out to be? 265.
You deem it as significant.
Okay. Okay. So hang on a second. 265. What was it? Point what?
357066.
Okay, that's good enough for now. Okay, good. All right. So now let's talk about significant digits. Okay. So now if I measure, let's say I took 100. I sampled 101 liters of air, and I found 0.25000 25697. I'm going to say 100, exactly 100 liters. 0.29697 milligrams per liter. I'm going to just make that up for a moment. And I want to know how many milligrams were in that 100 liters of air. If it's 2.25. So normally you just say, I'll multiply by 100. So there's 25.697. Well, you may have measured the weight to 3 decimal places, but you only know the volume to 3 significant digits, right? So your answer cannot be any more accurate than 3 significant digits. So your answer here would be 25. If you want to round it, your answer would be 25.7. Okay. So whatever is the smallest number of significant digits in your calculation is how many significant digits you should round it to. So if you have a calculation, 2.2 times 10.973 times 11.547 times 16.12934, right? And your answer comes out to be, I'm going to make a number up, 34.79263 or something like that in Excel. How many significant digits do you actually know that to? Only 2, right? It'd be 35. You'd round it to. Right? Because you don't know, even though you know all these things, the more to that level of accuracy, there is one part of it that you don't know to more than 2 significant digits. Right? So that's how you figure out how many digits you should round to. The other thing you should remember about this is never round until you're done with your calculations. So what happens if I say 2.3 times 2.31 times 4.6578 squared, right? If I take that and I say 2.31 times, I'm only go 3 significant digits, 4.66 squared, what happens here? You multiplied your error in the process of doing this calculation. Even if it wasn't squared, you would double your error because you're multiplying by 2.3, right? So you would keep all of your digits until the very end and then decide what to round to. Okay, that makes sense, right? Because if you round any of those numbers before you get to the last number, you can compound the error by multiplying it by something, by dividing, by squaring it, and so on and so forth. So keep all the digits till the very end, and then at the very end you can round. Yes.
When you have 27.7.
Yes.
And what made you decide to round it to 7?
Where did I do that?
You have 245.67.697.
Yes.
So you round it up to 7. Why?
Because it's 6.9, right? So that would in other words.
Why don't you keep 2 digits? Because you have 27 in the front.
Yeah, but see, if I did that, I don't really know if that's right. Right? Remember, because I only know this correctly to 3 digits, right? Because I only know 3 because I know this is not 101 and I know this is not a 99, but it could be 99.8, right? I only know this to this number of digits.
So you use the reference based on the 100.
I only want it to 3 digits, but I do know that that last digit after it is a 9, so I would round that. I wouldn't just truncate it. I would use that extra digit to round. Right, so 25.7. But I only reported as 3 significant digits.
Why didn't you do the same thing for 34?
What did I?
You ran it up to 34 point.
Where is it?
The last one below, all the way down.
34.7. What did I say? 35. Yeah, I rounded it up.
So
35.
all the way to 35.
It's only 2. Yeah, because I instead of saying 34, I rounded it to 35 because 7.79 was the digit after that. Right? I used to work in a lab.
Yes, 2.2 is the smallest number.
Exactly. That's your least accurate number. That's your least significant digits. Exactly. So nothing can be more accurate than that, right? In other words, it doesn't matter what the accuracy is for any of the other measurements that your calculation is based on. You're limited to 2 significant digits because of that measurement, right? I used to work for a company where the guy in the lab, you have, they're all automated now. So you have these probes that go in and it prints out and connects to a computer and this, that, and the other thing. And he had a pH and a TDS probe, right? And a pH probe would give him a reading of 7.492, right? Now, there's no way in the world that pH probe is really reading 7.492. Right? It's just that's what's coming out on the scale. But I mean, the thing is plus or minus, it's plus or minus, 0.01 pH, right? Or so 0.03 pH. So to report that way makes no sense, right? Because it's not even though it's that's what's coming out on the display. The instrument can only be relied on to report plus or minus 0.03 pH. So you really should round that to at least 7.49, probably 7.5, probably be good enough for any kind of normal work that anyone would do. But at any rate, yeah, that's always a thorny issue, But and you'll see in reports all the time. Some reports, this was 200.794 ppm. I'm willing to bet there's no way in the world that that every measurement he took to get to that calculation was 6 significant digits. Right? So, but you see that constantly. People don't like to round. They either like to round, or they either don't like to round at all, or so it makes the result of the calculation seems more accurate, more precise than it really is, or they round without like any real rationale on how to round it. And really what you should look at is significant digits when you decide how to round. So sorry to go off on a tangent there, but it's a personal bugaboo of mine when I see. What's that? Oh, 1 significant digit? That's a problem. Yeah, right. Well, but that, I just make 100. It'd just be 100. Yeah. If it were 124 times 1, right? Then you have an issue, right? Yeah. I would. Yeah. That's the problem. That's really a measurement problem more than anything else. Yeah, because you don't really know if excuse me. Yeah, exactly. What is that? Right. Is it really 1.8? Is it really 2.2? Is it, if you only know it if you only sample 1 cc, 2 cc's, and this is what you got, then you got a problem. Unless you know that your measurement of 2 is more accurate. In other words, if you know that the device, one of the things I have here is a micro syringe. You can measure out a microliter of liquid with this device, right? So even if I say if I say 1 liter, 1 milliliter with this device, it's really accurate enough that that 1 liter is really 1.000 milliliters. You know what I'm saying? In other words, just because the number's 2, yeah, in other words, is it 2 times that, or is it 2.000 times that? Right? That would be 4 significant digits. Right? 2.00. If the measurement you take really is 2.000, then it would be 4 significant digits. Thanks for confusing everybody.
Just to clarify.
We had it so well until you brought up a good point. Yeah.
You have 2 numbers,
Yes.
243
Yeah.
and 2. How many significant figures do you
Only one.
one?
Right. Only one. But that's a prop. That's a, you know, I would, in that situation, I would probably, I'd probably just say 46. Because I mean, that, you know, that's like such an imprecise measurement. You know, that's such an imprecise measurement. If, you know, for instance, if it were 240 million, if we're 24 million times 2, right? I might be tempted to, instead of saying 4.8 times 10 to the 6, say 5 times 10 to the 6. Only 1 digit, only 1 significant digit, right? I might be tempted to do that, you know, but I mean, with those numbers, you're probably never going to run into that, because usually any kind of measurement that you would take seriously is going to be a little bit more precise than that. But the whole point is that any calculation that you do is only as good as the least accurate element to that. And that's what you should examine in terms of if you're going to round it, how to round it. Okay, let me get back on track here. Okay, so that's how we calculate that, right? So, and we're going to get another shot at this also. Okay, play from current slide. Oh, I should, okay. Okay, so how do we measure this stuff now? Okay, how do we actually measure how much of this stuff is in here? One way is to use that sorbent tube device, right? Is to actually suck the air through that tube, find out, get it absorbed into that tube, send it to the lab, go through this calculation. We know how many ppm that's in there. We can also use a number of other strategies to do this. This is just some extra stuff you can take a look at if you need conversion factors and stuff like that. One method is to use a bellows or piston pump to sample by drawing air through a detector tube or colorimetric tube. And we have some of those here. How many of you guys used Draeger tubes before? Good. Okay. Good. I'm glad. I like it when only one person holds up their hand, because that means that there's a reason we're doing this, and you know, I'm not wasting my time. Let's hang on. Wait. Pull that back for a second. Those are one kind of tubes. Okay. Yeah. You know, I think I have some separate tubes here. Okay. Mixed tubes. Want to hand this out? Yeah. Oh, that's going to cause a problem. No, that's. Here we go. I think I got some here. What it looks like. I know I have some in one of these things. Okay, you can send these pumps down there. So taking a look at these pumps. I want to hang on to one. And one of these, you know, what's that? Yeah, I believe it. No kidding. Why do you do that? I don't think you need to refrigerate. Oh, there you go. That's it. That's it. Yeah, that's it exactly. Okay, I'm gonna take one right here that we might actually see a measurement on. Usually, I don't have any CO2 ones. CO2s I'll always have. Basically, you have these tubes. You'll see, I'm gonna pass them around, and you will see that there are graduations on these tubes. This particular tube is for, this tube is for sulfur dioxide. And sulfur dioxide is, emitted from smokestacks and various combustion sources. Cars used to emit quite a bit of it, not so much anymore because of the catalytic converters. But sulfur dioxide is a noxious, irritating gas. And what happens is the material that's in this tube will change color in the presence of sulfur dioxide. So this bellows here, this pump, this air pump, is designed so that when you squeeze it completely, it will draw a tenth of a liter of air through this hole in the top. Okay. You see, one of the ways to test to make sure it's working correctly, squeeze it together, put your hand over the hole. If it starts to move apart, you know something's wrong with it. It's not the little check valves in it, or little rubber check valves in it are not holding air. So we want it to hold air so that when we put a tube in here and we start pumping, when we pump it, it sucks a tenth of a liter of air through this tube. Each of these tubes comes with instructions. They actually mark them on the outside of the tube. This particular tube has, I don't see it, but it's on here somewhere. This particular tube is graduated in parts per million. And in order to take a reading, we have to pull 1 liter of air through this tube. So 1 liter of air through this tube would be 10 pumps, right? Okay, so in order to pull it, it's sealed. So in order to pull air through it, we have to break the tips on either one of them. There's a little abrasive pad on all of these, on each one of these things. You can use that to kind of score the tip and then bend it in there and it pops off. So it's open. Okay. Try to keep track of where the end goes. So now this tube can go in here. Okay, there's an arrow in there to give you the direction of flow. This tube can go in here, and we can start pumping this tube, 1/10 of a liter of air, right? And what will happen is there's a little white dot in here. When that turns white again, you know it's expanded completely. Okay, that's 1/10. So we would actually count these. Some of them actually have a counter on them, so you can keep track of how many times you pump it. Okay, so I'm going to take this one out. You can just to show you can pass that around, see what that one looks like. I am going to put in a carbon monoxide tube in here.
I was wondering how you break this thing. I was gonna break it with my hand.
This one's methanol. Yes. What?
Are we supposed to break that?
That's the one I just passed around. I already broke it,
Some
right?
are broken, some are not.
Yeah, it comes unbroken. You're supposed to break them and then take your reading. Hang on a second. I'm gonna send one around that's a little bit more interesting. What happened to the? Did you send that? Do you guys have the carbon monoxide? I didn't mean to send those around, those tubes. Who's got the carbon monoxide tube? Well, is there one with carbon monoxide tubes? Let me see if this. It looks like all the other tubes, except there's carbon monoxide on it. Yeah, these.
Right there.
Huh? Is it opened or closed? Okay, good. Okay, so I'm gonna take this one. I'm gonna zero this counter. Use the end of the tube to zero it. Okay, and I'm going to start a tube. Okay, and let's see. It says, let's see. N equals 10, means 10 strokes. Now, this American company makes another version of these. American Sensodyne uses a different kind of pump. It looks like a bicycle pump. Yeah, it looks like a bicycle pump, kind of draw air through it. And they also have automated versions of these where you can push a button, it sucks a liter of air through it instead. Okay, so I'm going to start this one. And you'll see what will happen is if there's carbon monoxide present in the air, you'll start to see a blue color develop. Okay, so my guess is, we're at the 6th floor here. My guess is, at the most, we might find 1 ppm of carbon monoxide. right? If you are down on the street on 125th Street in traffic, I'll bet you'll find 2 or 3 ppm of carbon monoxide. It's a little later now. If it was like rush hour, I think for sure you might. Okay, so I'm going to start this. I'm going to take 2 strokes on it. Everybody takes 2 strokes. It's designed for only 10 strokes. That's when you should take your reading. But if you keep doing it, you'll see the color change. It'll help you see the color change of this thing. So I'm going to take 2 strokes on here. And you wait, just take the strokes, squeeze it completely, use 2 hands if you need to. Wait until that white dot reappears. Okay, it reappeared. So I'm going to squeeze it again, and that's my second stroke. So you guys each take 2 strokes. Wait until the white dot comes back. What's that? That works exactly the same way, except that you don't have a counter on that one. You have to count it yourself.
So,
Yeah, we're very poorly supplied here.
the white comes on. You like the 2 strokes, that's 1.
Yeah, I don't know how many strokes of sulfur dioxide is.
The tube that I have doesn't have a direction.
Oh, no kidding. It should be clear, right? I mean, it should be like something to pack it in or something like that. Should be able to figure that out.
It's only like half a tube too.
Oh, no kidding. Maybe there's something wrong with it.
No, I don't think so.
Sulfur dioxide, was it?
I don't know. No, it doesn't look like that.
Yeah, pass that around. Everybody take 2 strokes on that thing until we develop a color.
And see, I think that,
The white dot is like.
yeah, it's,
Some of these I can't even tell what they are. And there must be 1,000-year-old tubes, because some of them don't even have the number on them.
They expired like 5
Yeah.
years.
Now that you mention that,
Well, yeah, they do.
Well, I don't wait until it's like white.
they're so old that it's before expiration dates.
That's the tube that, yeah.
What is this one?
This one is
There's
a
no
good question.
direction on it, and it doesn't. No idea.
This might be a sorbent tube. Yeah, this is a sorbent tube. You know how, come back here. Come back here. How do I know this is a sorbent tube? Take a really close look at it.
It looks like cotton sided.
Take a really, really close look at it. That's 10x.
So you got the 2.
Right. You have a backing, right? The backing's half the size of the unit. So we're going to talk about backing eventually. If you look at this really, really closely,
Yeah,
you can
there's.
see there's material, sorbent material,
And
then
then-
there's packing, and then there's more sorbent material.
Mhm.
And it goes this direction because that fat one is where you're going to absorb the VOC, and then it keeps going through. In that second section, you analyze both of them separately. If you find any in that second section, you know that it didn't capture all of it first. So you throw it away, start again.
so you don't count it as a break.
So this thing
It's
goes like
it's called
this?
breakthrough, right? Yeah. So we'll talk about that in a second. No, it doesn't go there at all. This would connect to a pump.
Oh, okay.
It's a sorbent
Not-
material.
not for this.
It's just not activated charcoal. It's a different sorbent material. My guess is it's 10x. Right? So you might use that for a different organic chemical than the ones we're talking about. Okay? Okay, guys, let me get back to this. Okay, so notice on the bottom there, they have literally hundreds of these tubes for specific applications. Sulfur dioxide, for nitrous oxide, for many industrial chemicals, solvents, chlorine, acid gases. You name them, they have a tube for it. Okay, now, what do you think usually that the ranges that they use these tubes would be? They usually be ranges that would be in the range of the permissible exposure limit. Like on carbon monoxide, the tube you're using probably is 0 to 50 or 0 to 100 parts per million, because the permissible exposure limit is 50 ppm. Okay, so now, what do you think the accuracy of these tubes? Anybody want to hazard a guess as the accuracy of these tubes? Plus or minus 25 to 35%. Some tubes 35%. So you could say to yourself, what good is it if it's only accurate to plus or minus 35%? Well, think about this. You're using this as kind of a preliminary screening tool. So really what you want to know, am I anywhere near the PEL? So if the PEL for toluene is 200 and you measure 20, right? Well, geez, 20, I'm at 1/10 of the PEL. It doesn't matter if it's plus or minus 35%. I'm so far away from the PEL. Now, if you measured 150, you say, oh, could be that, there's enough range here of inaccuracy. It could be over 200. So now you have to go to a better technique, a more accurate technique, right? So it doesn't really matter for the kind of application you would use this for. You can tolerate that level of error. How are we doing on the carbon monoxide? Anybody see a color change on it yet? Got to keep pumping. And you know what you do? Tell you what. Okay, I'll take. Okay. Okay, so I was going to say, let's take a break, and somebody will run down the street with that thing, but just keep pumping. It'll turn a little blue. Okay, but I want to take a break because we really don't have a lot of time in these sessions. Okay, so now what's another way of measuring the amount of VOCs that in the air? And that other way includes devices that we can use to capture the VOC in the air or to directly measure the amount of VOCs that are in the air. Okay, so, and we have one here. One of them is a device called a photoionization detector. When you're an industrial hygienist, they're going to say stuff to you like, get the PID, right? That's a photoionization detector. Believe me, no one will ever call it a photoionization detector again, right? They'll call it a PID. Or they'll call it a mini ray or an ultra ray or something like that. That's this device right here. We're going to talk about how this works. I want to do this without breaking anything. Okay. Okay, so here's an instrument. I'm going to turn it on. It goes through a self-test when you turn it on with like a lot of other instruments. I'm going to put this on. It's just an extender, a probe extender, so that you can get into tighter spaces. Also has a little tip there where you can make connections easily if you need to take a sample from some device or a bag or something like that. So it's starting up and it's going through its self-check and so on and so forth. Now, how does this thing work? Okay, well, what happens is that this thing is drawing air in from the room. And there is a cell inside this device where there is a very strong UV light, ultraviolet light, high energy ultraviolet light. Actually, you can buy these things with different kinds of cells. 9 electron volt UV light, 11 electron volt UV light. That's the amount of energy that it can produce. So what this does, that high intensity UV radiation will excite the electrons in a molecule, so that if you look here, as this gas that's in the air, the VOC that's in the air, not going to affect oxygen, nitrogen, the stuff that's usually in the air, not going to be affected. But as that VOC goes through this cell where it's irradiated by this UV lamp, right, it knocks electrons off of those molecules. That ionizes the gas, turns into ions. Ions are conductive. Normally, organic molecules are not very conductive. They don't conduct electricity very well. Now it makes the air and the air that's with the gas in it passing through it, makes it more conductive. More gas there is, more conductive it is. And you have a device that measures the conductivity, and the computer in here converts that into a parts per million reading. Now you might say to yourself, well, Tony, if it's methane that's in the air, will it read it? I got to go through a list of compounds because I don't know if this has enough energy in it to ionize methane. Will it read alcohols like isopropyl alcohol? Probably yes, because it doesn't take much energy. I just happen to know it doesn't take much energy to ionize that. So depending on the instrument you have, you may not be able to read all different organic compounds in here because it may not be able to excite them. Well, the other thing is that, well, gee, some molecules, when you excite them, you'll knock off more electrons. It's a bigger molecule. The conductivity change will be bigger, right? So how do you know that the level is 200 ppm for isopropyl alcohol, and then for toluene, it's a different conductivity, right? It changes according to the material you send through here at the same concentration. 200 ppm toluene is going to be more conductive let's say then isopropyl alcohol is going to be, for instance, maybe the other way around. I don't know. So how do you know that? Well, what you do is this instrument is calibrated to a single gas. The only thing it reads perfectly is a VOC called butanone, right? Butanone, it's like butane, right? Butanone, what is one? One is a ketone, right? So butanone is a ketone, right? So what we have with this kit is we have a standard gas. This is our standard gas. This container contains air, it has air, has clean air. Sometimes I have nitrogen instead of air. Has clean air with exactly 100 ppm of butanone. So if I had the regulator, I could connect the tube to this, connect it to the end of this, and what should it read? It should read 100 parts per million. If it doesn't read 100 parts per million, I calibrate this so it does read 100 parts per million butanone, right? So the only thing it reads perfectly is butanone. However, this comes with a catalog from the manufacturer that tells you that if you read 100 ppm of butanone and it's properly calibrated, if in the air instead of butanone it's isopropyl alcohol, well, 100 is really 50 ppm. In other words, there's a conversion factor. And it has a catalog for all these different organic VOCs that it can read. Now, remember, it can't read all of them because it depends on the energy of the lamp. Can't read all of them. But it has a catalog, the ones it can read. So if we know we're only dealing with the presence, in a lot of workplaces this is going to happen. You know that the guy's working in this area, the only thing he's using is toluene. Right? Or the only thing he's using is MEK, for instance. Right? If you notice the only thing he's using, you can look up the correction factor in the chart from the manufacturer, and you can say, well, if it reads 75 in here, the correction factor is 1.2. So you take 1.2 times 75, and that tells you how much MEK, how much methyl ethyl ketone is present. Okay. Now, I just told you the way we work on a 30-year-old instrument like this. Nowadays, these have the tables, correction factors built into them. So you can actually program this to, okay, it's calibrated for butanone. Now read back in what it is for methyl ethyl ketone. So you don't have to go to a chart to read it. Personally, I use the chart anyway because I hate recalibrating these things and reprogramming them. So it's just easier, just use the chart and say, oh, I know it's isopropyl alcohol that's in the air here. So this is the correction factor. If it says 100, it's really 80 or something like that. So I'm going to pass this around so you can see this. And as I pass it around, I will also
What I've seen is,
I think I put it in my pocket.
So this thing measure combination of concentration and single concentration?
It measures concentration of an organic chemical in the air. It doesn't know what VOC, what organic chemical. It just measures organic chemicals, right? So you know that this, if you calibrate it for the calibration gas and it says 100, you know that if it says 100 when butanone's in the air, it's really 100. If it says 50 when butanone is in the air, it's really 50. But if you're measuring a different gas because it's calibrated at butanone, you have to apply that correction factor. Okay, so now, I don't know the best way to do this. I think the worst way to do this probably is to pass around that bottle because you know what's going to happen next. I wonder if I have, anybody got like a napkin or a tissue or something?
I have
Something on the back end.
Huh?
You want Sharpie?
Yeah, you think it's a show? No, I think he's got a great idea then.
I have a home.
Okay, here. What's coming off that Sharpie? Anybody have any idea? What's in that Sharpie?
It's alcohol.
Can you smell it? Is it alcohol?
Let's find out. Well, you can't tell you. You have to know what it is. You can't tell you what.
I'm not picking much up. You know what it is? What's that? Oh, okay, so that's gonna be alcohol. I'm gonna pass this around with the Purell. I just have to stick it. Yeah, pass it around. What do you have on your jacket?
It's not, it's just deodorant.
Oh, deodorant. Okay, yeah, VOC, right? Okay, So what's another good application for this? It'll measure any VOC. If you have an unknown source, an odor complaint, let's say, what can you do with this? You can kind of use this as a sniffer, walk around, see what the highest concentration is, and try and find a source for an odor. Does it ever work? No, never. You never actually find it.
What's that cost?
What's that?
How much does that cost?
That's probably a few grand. I guess anywhere from, depending on what kind of lamp it has in it, and how programmable it is, and the catalog in it, anywhere from say $3,000 to $10,000. And however, you can rent that instrument probably for less than for about $100 a day, or for about $300 a week. Right,
What's
so-
the accuracy for
The accuracy is I'm going to guess like at least 1%, plus or minus 2%, 2% or something like that. That's a wild guess. Yeah, they're quite accurate. Okay, so that's a photoionization detector. It uses a lamp, a light source, to energize that molecule, to ionize that molecule.
The key with those.
If you want, you can push that. Try not to slow it. Okay, if you want to hold it over the isopropyl alcohol, you can do that. Okay, so that's a photoionization detector. That's one of the most useful tools for measuring VOCs. And what kind of instrument is that again? What do we call that kind of instrument? That's a direct reading instrument. Okay, so everybody get a chance to play with that thing. But remember, the way you calibrate it is you use this standard gas. I don't know if it's got the regulator in here. How do you zero it? Anybody want to hazard a guess on how you zero that? What's that? Oh, yeah. But how do you know that it's reading zero correctly? How do you calibrate it for zero? What kind of air do you have to pull through there that should be reading zero? You have to have air with no VOCs in it, right? That would be zero. Where are you going to find air with no VOCs in it? Right. Well, you could buy a canister like that, but if you don't have a canister, where are you going to find that? What you do is it comes with an activated charcoal cartridge. You put an activated charcoal cartridge on the end of that, and that basically gives you clean air from the perspective of VOCs. Okay, it's going up.
The number is going up, but how do you basically, let's say right now it's a lot of volume going on. So how do you know? Does it calculate the volume or does it calculate?
Oh, this is parts per million. This is literally parts. This is a direct reading instrument. What I'm reading right now is exactly how many ppm of that VOC is in the air. Right. So it's like I said, literally direct reading instrument. Okay. So if I go into a workspace where they're using, if it's calibrated for a methyl ethyl ketone, MEK, if it's calibrated for that gas, if I go into that workspace, I could hold this near the worker's breathing zone and I could read what his exposure is, right? Okay, and if it's calibrated for isobutanol, right, I could take a reading also for methyl ethyl ketone, but I'd have to multiply it by the correction factor. What's the downside of this direct reading instrument? If you don't know what the contaminant, exactly. If you don't know what the contaminant, it doesn't really do you any good because you're going to read a VOC, you don't know what it is, right? What's the other downside of it in terms of measuring occupational exposures for OSHA? It's not an approved method. Why not? Because OSHA is interested in a workplace exposure, 8 hours. What are you getting here? You're getting an instantaneous reading, a direct instantaneous reading. So all you know is what the level was at that moment. Now, it's very unlikely you're going to want to follow the guy around by sticking this in his face for 8 hours, right? So this really doesn't do you much good in that situation. Now, this is, again, it's programmable. It has memory. It'll store it. Has a timer in it. You can tell it when to go on, when to go off. It's great for area monitoring and so on and so forth.
I have the same question. I really think that.
What lamp? Do you know what lamps in there?
That's a good question. Hang on a second. Yeah, I would think it's the middle. It's a 9 point something, 10.6, and 11 point something. And I don't think I have the chart. I'm going to do the chart. I got a couple of videos I want to show you, but we're not going to get to that. energy in the bulb that's in here, in the UV bulb that's in here, determines what kind of molecule you can excite so that it will ionize. So if you have a 9 electron volt lamp in here, right, there are going to be compounds that this light is not strong enough to ionize, so you can detect them. So you would need a 10.6, but even at 10.6, there's going to be more compounds that you won't be able to ionize. So you get 11.2 or whatever it is, electron volt lamp, and you'll get a more device. So you might say to yourself, why don't you just buy 11.2 on everything, right? Problem is that those higher energy bulbs, they cost way more money and they burn out faster, right? So there's a cost issue there. Okay, and there are many molecules, many volatile organic compounds that will not ionize with any PID, right? So you can't, methane, I think, is one, for instance, that you can't read with a PID. I think, I'm not positive. You can look that up. Yeah, I don't know what it, I'm not sure why, but I forget. I'm pretty sure it's that. Yeah, it's a higher energy, maybe possibly formaldehyde too.
I think formaldehyde, yeah. Or you need the sensitive bulb to pick up formaldehyde.
The highest energy one.
Okay, as an inspector, so using this equipment here, so it is. I don't think it's as accurate as you.
Oh, it's very accurate.
Well, accuracy, but let's say, for example, you're sitting right here, and the exposure is more that or more close.
Oh yeah. Again,
you can't really get that much.
Well, you go over there and measure it. In other words, if you're going to use this, you're going to be looking for the place where the exposure is greatest. So in other words, if you're concerned about let's say a metal cleaning operation, you're going to measure where the worker is next to the tank. You know, in other words, he's not going to measure across the other side of the shop. You're going to measure where he's working when he's at the tank. So you're going to measure his breathing zone there. And you probably say to yourself, that's probably worst case. If he steps back 6 feet, it's going to be lower, right? So when he's right at that tank, that's where the highest exposure is. So you can use it that way. But really, if you want to really know what his exposure is, you really need to measure it over an 8-hour period. And for that, you would use a sorbent tube, right? However, there is another way around that as well. Oh, okay, good. I thought you were giving me a drink. I was going to have a sip. I don't think this is the right alcohol for that. Okay. So another method that we have of determining VOCs in the air are passive dosimeters. They're badges. They're devices that will absorb the material that's in the air. So for instance, this is a badge. It looks like the one that's made by 3. It doesn't say 3M on it, but it's very similar. And what is this? This is a device that has a whole bunch of little holes in it, a little screen in the front. But behind that, it has a packet of activated charcoal. So you can wear this during the entire 8-hour workplace day on your collar. And if you're in an area where there's a very high level of a VOC, like formaldehyde, or formaldehyde is a little special. I'm not sure to use activated charcoal for formaldehyde, but I don't know, glutaraldehyde or some other methyl ketone or benzene, for instance. Benzene for sure is absorbed by activated charcoal. If you're in an environment that could have some benzene in it, if the concentration in the air is high, by diffusion, it will get absorbed onto that activated charcoal over an 8-hour period. At the end of the 8 hours, you take this, you seal it in an envelope, you send it to the manufacturer. Their laboratory analyzes that activated charcoal, determines how much benzene was absorbed from the air, and based on their studies, they study it in environmental chambers. If this in 8 hours, if you have 10 ppm of benzene in the air and this sits in there for 8 hours, this is how much we expect to find in this activated charcoal. If it's 100 ppm, this is how much we expect to find. So they've calibrated these devices for that kind of environment. You tell them how long you had this exposed for. You tell them what the temperature was, what the humidity was when you did it, because activated charcoal can absorb moisture from the air as well, which can make it harder for it to absorb other stuff, right? So they take all of these things, they do a multivariate analysis on this thing, and they predict how much must have been the average concentration in the air while the worker was wearing this thing over that period of time. So these are badges or passive dosimeters. You can use them as an area monitor. A lot of people do in their air quality. They'll clip these to some spot in a room or something like that to come back and collect it after 24 hours, and they'll send it to a lab. And the lab, they can ask the lab to analyze it for specific VOCs, toluene, benzene, whatever, if that's what they're looking for, or they can ask them to give them an idea of what the total VOCs were. How much was the total weight of volatile compounds that this absorbed from the air, right? So total VOCs, a lot of people say, oh, if you have over 1 ppm total VOCs in the air, that's unusual, right? Is it bad? Well, who knows why you just have it in the air? It might be bad, might be good, who knows? But I mean, if you're in a hospital and you're using a lot of disinfectant, that might be a good thing, But but if you know a normal office environment, you wouldn't expect more than 1 ppm of total VOC in the air, for instance, right? Just rough rule, right? So you can use it that way. They're not just used for VOCs. You actually use it for radon, right? Because radon is a gas. It's absorbed by activated charcoal. You buy a new home. You buy on the left there, it's a sorbent packet. You open it up. You leave it in the basement. We'll close up the windows in the basement. Leave it in the basement for 3 days. At the end of 3 days, you close it up, send it to a lab. They analyze how much radon has been absorbed by that activated charcoal, and they predict how much radon must have been in the air in the basement of that home, and let you know how hazardous it is, right? So you need something you can do quick. On the other side, there's something called a track etch meter for radon. The way that works, it's got a little piece of film in it, a little piece of plastic, and as alpha particles hit it, right, as the radon decays and alpha particles hit it, it gets a little track in it. So they can actually leave that in the basement for months at a time, then send it to a lab, and you get much more representative analysis of how much is there. So these passive air samples, they don't rely on any active flow of air. You're not using a pump, doesn't use any. So there's a compromise in terms of how many different compounds you can analyze with these things, and there's also a little bit of concern about how they work, because if you got a high exposure early in the day, the activated charcoal might absorb it, and then if there's no exposure for the second half of the day, you might actually lose some from the activated charcoal. It might go the other direction. So that they have their issues as well. Okay. Now, just one thing I wanted to mention is that these things, notice it has like this cover on it. There's little holes in it and stuff like that. A lot of these don't use that. They use a pad across the front of it. Some of it just looks like a solid piece of plastic, but that plastic is permeable, right? You got to read the instructions carefully. A lot of people pull that off because they think the activated charcoal behind it has to be directly exposed to the air. That diffusion pad has to stay on there. So when you get one of these things, you're going to use it. Read the instructions very carefully. You got to do it precisely the way that the manufacturer wants you to do it. So air sampling, sorbent material. Here's our sorbent tubes. And I was just about to start talking about, okay, let me see if I got a good, here's a good picture of a sorbent tube. Now, here's our sorbent tube. The air is going this direction. They sell these sealed up. They have to be pure activated charcoal, no VOCs in them, because you don't want them contaminated before you get them. So on this end over here, you would break off the ends of these tubes, just like you did for the Draeger tubes. Connect this side to your pump. Connect this side to your pump. So you're sucking air through the end here. There's nothing in front of this, right? So you might put it into a holder or something like that, but the air is coming directly in here. The air is passing through a section that has 100 milligrams of absorbent material. In this case, it's activated charcoal. You see black, so it's activated charcoal. That's got like a little fiberglass pad in there, or cotton pad. Then there's another section that has half as much. That's 50 milligrams of activated charcoal. And then that goes to the pump. Okay, now the flow rate is important, because you don't want the flow rate to be so fast that you pull it through here before it can be completely absorbed into this front section, that 100 milligrams. You can pull it through too fast. You ever see those little filters you put on the end of your spigot, on the water filters, a little activated charcoal filter? You screw it on the end, it's got a little about that big, and you turn the cold water on, you get a glass of water, it's supposed to take everything out. That's impossible. the water's blowing through there so quick, there's no shot at taking out all the chlorine and all the, and so on. So you need a good sized volume of activated charcoal to take all the flow, at the flow rate that you would deal with realistically. So that's the same thing here. That's why when you read the method, when you take a look at the method later on, it's instead of saying 1 liter per minute, 2 liters per minute, like we said for particulate, instead of saying 15 liters per minute for area monitoring, for asbestos or something like that, it's going to say 1/10 of a liter per minute or 2/10 of a liter per minute. So you want that to move through that slowly so it can absorb that VOC completely, right? Otherwise, what will happen? It'll pass through there without getting absorbed, and some of it will get caught in that backing material, 50 milligrams. What else could go wrong? Well, if there's a lot of VOC in the air and you run it for a long time, you could saturate that activated charcoal so it can't absorb. Well, eventually it gets to the point it can't absorb anymore. What happens? The VOC passes through there and it gets absorbed into that second section. So when you send this to the lab, they analyze both sections. If the backing has, I don't know what the rule is, you have to look at the method. I think if the backing has more than 5% of what's in the front section, right, the sample is questionable. It indicates that you've had what? Breakthrough. In other words, you haven't captured all of it in the absorbent, in that absorbent material. Yeah, now this one is called 10X. You can pass this around. If you look carefully, it's like this activated charcoal tube, and you'll see 2 sections, except 2 sections. One is, it's flowing this way, big sections in the beginning, flowing this way, because the big sections first, the little sections, you see there's 2 sections of that sorbent material. So send that back around so I can take a closer look at that. Okay. Except that it's a white, have you guys seen that? Did you see that there's 2 sections? Yeah. I just want to make sure you saw that there were 2 sections. Okay, so there's your sorbent materials and so on and so forth. And there's different kinds of sorbent materials. Silica gel for polar compounds, 10X for nonpolar. You're not going to worry about polar and nonpolar. You're going to look up the method for what you are trying to measure. Yes. Okay, how are we doing here? Eek. Shit. Okay, so now remember I mentioned that like a lot of times you don't want to have to do this again. If I don't know how much VOC is in the air, it would be very easy for me to not sample enough air or sample too much air, so I wind up getting breakthrough, or I don't wind up getting enough for the lab to detect it. So it's good to take more than one sample at the same time. So I said 1/10 of a liter per minute, 2/10 of a liter per minute. So we have devices that will allow you to, ow, thing bit me. I'm gonna pass this around. Okay. Okay, if you look at this, there are 2 screws, one on this side, one on that side. You connect this to your pump and you calibrate. You put your 2 tubes in here. You calibrate through the tube, right? And you can restrict the flow in each side separately. So you can set this tube so you're drawing 1/10 of a liter of air per minute, and you can set this tube so you're drawing 2/10 of a liter or 3/10 of a liter or 0.05 liters per minute, or whatever volumes that you want, so that you have a better shot of matching the flow rate and the sampling time to the concentration that's in the air, so you're not likely to have to redo this. Okay, here, pass that around.
How do you do that? Because you have one pump.
What's that? No, you have 2 ports there. See those screws on the side?
So this is,
So you put
these 2 sides?
Yep, let me get it back. Right, you put 1 tube in there and 1 tube in there. And you adjust the flow rate on this tube using the screw on the side here,
Okay.
and you adjust the flow rate on the other tube using the screw on the other side. Okay, pass them out together. Okay, good. Okay, so here's calibration technique. Can you see that? Is that off the screen? Yeah, that's kind of off the screen.
So what tells you, when you're squeezing this, turning this electric,
You're connected to the dry cal. You're seeing the volume from the dry cal.
cal will tell you.
Yeah, that's what you calibrate. Just like changing the flow rate on the pump, except there you're changing the flow rate using those screws. Okay, now of course you have to have blanks and so on and so forth. So where's this stuff go? Okay, this stuff goes to a lab where they have to analyze how much of this organic material is absorbed on that material. So let's talk about gas chromatography. Eek, let me close. Yes,
But when I use this one with the two,
yes.
for example, if one of them give me 2 ppm and the other one gives me 1 ppm, what do I
Oh,
do?
no. They'll give you the right, both give you the right answer. In other words, if you have it at 2 liters, at 0.2 of a liter per minute, you have one at 1/10 of a liter per minute. The one that's operating at 0.2 of a liter per minute will absorb twice as much material as the other one. So when you do your calculation, it'll come out to the same number of ppm, because this will sample twice the volume, but it'll also capture twice the amount of material.
So I just use.
So you're only using the two volumes because you don't want to have to go back and sample again. In other words, if you sample at 200 liters, 0.2 liters per minute, and you get breakthrough, you got to go back again and say, oh, I should have sampled at 1/10 of a liter per minute instead. So now it gives you a little bit more leeway, so you don't have to worry about that. Okay, so let's talk about gas chromatography. Okay, so the lab takes your sample and it gets that bundle of stuff that you sent them, and it takes that activated charcoal out of the front and out of the back. It takes both of them, analyzes both of them separately, right? So it takes that activated charcoal and it puts it into a cc of some solvent that will remove the VOC from that activated charcoal. There's another way they can do this also, but that's usually the way to do it. They extract it using this solvent. Okay, so now your VOC is sitting in this solvent, very low concentration, very little amount on this activated charcoal, right? So it's sitting in this solvent. They take that solvent. I'm going to make believe that solvent is methanol. It's not, but I'm going to make believe it's methanol. Okay, they take that solvent, so it's methanol, and it's got your sample. Let's say your sample is acetone. Okay, it's got methanol and acetone in it. Okay, so now what's going to happen now is it's going to take that and you're going to inject a small, tiny amount of that. That's what that micro syringe is for. You're going to inject a small, tiny amount of it into a gas chromatograph. Okay, they're going to draw this. It's a rectangular machine. Usually they're a couple of feet high by a couple of feet deep by a few feet long. And inside that machine, I'm going to draw this for the moment a little bit incorrectly. In that machine, we're gonna inject it into a port over here. That port is connected to a source, a cylinder of an inert gas. Could be helium, let's say, right? Okay. And then as you're injecting it in there, we're pushing helium through that port as well. And then through a long tube. That tube has a sorbent material in it. Could be TEDx, could be activated charcoal, could be silica, could be a lot of stuff, right? So what's going to happen is it gets absorbed onto that tube. By diffusion and by some of the energy imparted to it by the helium we're pushing through there, that VOC migrates through this tube until it gets to a detector at the other end of that tube. That detector could either be a PID or it could be an FID. What do you think an FID stands for? Flame ionization. Uses the flame. In fact, usually there's a cylinder with hydrogen connected to that, and you're using pure hydrogen gas to give you that flame along with oxygen or air, clean air. Okay, so that flame or that PID excites that molecule of organic material, and there's another device right after that measures a change in conductivity. So what happens is that you can connect that now to a gauge, to an ammeter, to a conductivity meter, right? And as you start pushing the helium through here, the sorbent material, depending on its volatility, molecular weight, so on and so forth, different organic compounds will go through this medium, through this packing material, go through at a different speed. So methanol may take 2 minutes to go through here. So after 2 minutes, you'll suddenly see that dial go up. And then the methanol passes through, you see go back down again. And then acetone might take 3 minutes to get to the end here. Okay, and then you'll see the dial go up again. Usually they don't use a dial. Instead of a dial, they use a chart. And on the bottom of the chart is time. This is time. right? So 1 minute, 2 minutes, 3 minutes. And what happens is that when the methanol reaches this detector, right, you'll see a peak in this chart. That indicates conductivity went up. And then after 2 minutes, you'll see another peak, right? That would be the acetone. And then if you see another one, that might be a different VOC. They calibrate this machine so they know that if it took 1 minute and 38 seconds, that compound is likely to be MEK. Or if it takes 2.32 minutes, that compound is likely to be glutaraldehyde. And so that's how they calibrate the machine. It's the amount of time it takes to get there. Now, really, if it was just a straight tube, 2 feet long, it might be 5 seconds and 15 seconds. They'd be really close together. It'd be hard to distinguish the peaks. So instead, they take that tube, and instead of having a straight tube, they take a tube and they wrap it in a coil. You could have 10 feet of tubing, of packing material. You could have 100 feet of tubing here. What does that do? That delays this, so it separates these peaks out. It makes it more accurate. The larger the tube is. In addition to that tubing, it's important that the temperature be maintained very accurately because that influences how fast it's going to go through here. So that's in an oven that's temperature controlled the entire time that this is going on. So when you see that GC report, right, what's happening there is that those peaks represent when that material hit the hit the photoionization detector or the flame ionization detector. That's when it arrived at that spot. And the time it took to get there identifies what that material is. Also, the area of that peak represents the concentration. Now you say to yourself, gee, what a pain in the butt to try and figure out what the area of this is, by looking at it or on a grid or something like that. In fact, the machine you calibrate the machine. In other words, if you're looking for isobutanol, right, that was MEK, right? If we're looking for that compound, we would take a standard that we know has a certain amount of isobutanol in it, and we would run it through this machine and see exactly when it comes. We expect to see it at 2.32 minutes, and it showed up at 2.34 minutes. So we know that that's really where we should see it, right? So you calibrate this machine for these various compounds that you're going to measure, right? Each day, the calorie calibrating machine, each different compound they're looking for, they may be calibrating the machine. Okay, so they calibrate this machine to recognize that, and in fact, the machine has a library of compounds that it knows that if it's properly calibrated for isobutanol or something like that, if it's properly calibrated for that, then all these other compounds this one should show up at 1.1 minutes. This one should show up at 2.7 minutes, and it automatically labels that peak. That one is methanol. Let's say this one is acetone. It automatically identifies that peak for you, right? And maybe there'll be an unknown here. And if there's an unknown there, you can go and look at the time and go to your catalog, try and figure out what that might be. But that's how that GC works. Okay, so that's what happens. So what happens is they report back to you. In your sample, based on we desorbed it into the solution, we put it into the machine, and we found that you had 93 milligrams of acetone in the sample that you sent us. And that's what they tell you. Now, they don't know how many minutes you ran it for, what volume you ran through it, and so on and so forth. So they just report to you how much was in the sample. They also run your backing sample. Ideally, on your backing sample, you should only see the carrier. You should not see any acetone. Right? You should not see a peak for acetone. If you see a tiny peak, like 1% of what you measured in the front section, you might let that go by. If it's 10% or 20% what was in the front section, they might tell you need to rerun the sample, because clearly you had breakthrough. Either pulling it through the sample too fast, or saturated, the front section saturated, or something like that. So there's no way to tell how much was really in that, should have been absorbed by that front section. So that's the way that a GC works. Now, sometimes on the other side of this GC, they can further identify unknowns by using something called a mass spectrometer. And we'll worry about that. That separates things based on their mass rather than on the properties of diffusion through this tubing. Right? So maybe we'll get a chance to talk about that also. And I'm hoping maybe in the lab, maybe Bill at the lab that I'm talking about, maybe they'll have one you can actually see one. I don't know if you see it in operation, because like I said, it's a real ordeal to operate these things. You've got to calibrate them, get them set up, warm them up, and so on and so forth. And I guess we're out of time.